Okay, in 6.6, we're just trying to make sure you know the difference between what's a real number, a rational number, and an irrational number. And so we're just supposed to be, on this first set of problems that I put on here, we're just supposed to be saying, is it rational or irrational? All right, so what we have to do first is simplify these to know what they are. Now, the square root of 49 is 7. That is a rational number. So we'll just put R for rational. A rational number is a number, anything can be represented as a decimal, but it's a decimal that either terminates or repeats. And this is a decimal, 7.0 would terminate if you wrote it, so it would be rational. Now, square root of 50 would be, if you try to simplify that, you'd have to say, what's the biggest square in 50? Well, it's 25, so 25 times 2. Square root of 25 is 5, and then I've got a square root of 2 left. That is irrational. If you try to reduce the square root of 2, it is a decimal that never repeats or terminates. That's what makes it irrational. Now on 3a, you have pi plus 1 over pi. Well, that's just pi and 1 over pi. Well, pi is irrational and 1 over pi is irrational. This is just irrational. Anytime you see pi, it's irrational. Except for, look at 3b. What happens here if I simplify, though? Pi goes into pi once, pi goes into pi once. I get 1 over 1, which is 1. Well, that's a rational number because 1, or 1.0, is a decimal that terminates, okay? So looking down at 5. A, 1.23, that's a terminating decimal, so that is rational. 1.23, that's a repeating decimal, so that's rational. But C gives us an example of something that neither terminates nor repeats. The ... means it goes on forever, and we don't see any repeating pattern in there, and they're saying there's not one. So this is irrational. Okay, in problems 7 and 9, they want us to write each fraction as a terminating or repeating decimal. All you really got to do, and you could use your calculator for this, is divide 8 into 5, and you'd get, what, 6? And then 8 will go in there twice. Bring down a 0. Oh, it's 0.625. That is basically a rational number because it terminates. Now, if you do 13 divided by 7, let's see what happens to it. If you put it in your calculator, what you get is 1.857142, and then it starts repeating 857,142. And you're not going to see all of it, but you can see that it's repeating. So this much of it is repeating. So how you would write that would basically be 1.857142. This would still be a rational number because it does repeat. Even though it's kind of weird, it does repeat. Now in 11, they want you to write it in a fraction and write it to the lowest terms. Well, that's 5, and remember 0.06 means 6 over 100. Well, if you multiply that out and make it an improper fraction, 100 times 5 is 500. Plus 6 is 506 over 100. Now we can divide both of those by 2. 2 goes into there 253 times, and 2 goes into there 50 times. Actually, you can do this in your calculator, and it will reduce it for you like this, and it'll spit it out like this. So you could even do that in your calculator. And because that was a terminating decimal, we know that was a rational number. 13 is also a rational number. It is a decimal that terminates. So I could write 4 and 72 over 100, and then I can change it to an improper fraction so I could reduce it. So 100 times 4 is 400, plus 72 is 472 over 100. Now 4 divides into both of those. 4 goes into 472 118 times, and 4 goes into 125 times. And again, you could have done that on your calculator and gotten that. But that's what they're looking for there if you're confused. Okay, 15 is a little different. You can look at example 3 to see what they're kind of doing. This only has one decimal place here, okay? So here's what I can do. I can let n be this 0.4 repeating. Now, if I want to get, if I want to try to solve this, this has got one digit that repeats. So what I'm going to do is multiply. I'm going to say, well, what's 10 in? Well, that would be 4.4 repeating. And so then what they do is they come over here and they say, all right, take your 10 in and subtract n. Okay, well, what would that look like? That would be 4.4 repeating minus 0.4 repeating. Okay, so that would be 9n equal 4. So n would equal 4. If I solve both sides, if I solve for n, I would divide both sides by 9. N would equal 4/9. Now, if you put that in your calculator, it would actually do it for you if you just put .444 and put as many 4s as you could fit on your calculator and then put math enter. It would do that for you, but this would be the process where you'd go about doing that if you wanted to do it by hand. So you just multiply by enough decimal places to get the repeating part all by, where you can subtract it out. Like that's what I did right here is I had one repeating decimal, so I just needed to multiply by 10, and you could do this little subtraction, and you can find that answer that way. 17 is much like 15. If we let n be 0.83, repeating. All right, now, what I want to do is get rid of the repeating part, and there's one digit that repeats. So this is what I'm going to do. I'm going to try this first. Now the book says multiply by the given number by the number of 10 to the n. We're basically powers of 10, where n is the number of digits in the block of repeating digits. That didn't work so well here. I went off to the side and just messed around with this before I came back to record it. What I'm going to do, though, is it worked out. Here's how I figured out what to do. I have 0.83. I want to subtract 0.83, and I want the decimal part to go away. So I need to have like 0.83 where I can subtract it. What if I had this? What if I had 83.833? Actually, it would work the way the book says. Let's back up here. All right, if I let n be 0.83, if I write that out, that's 0.8333, right? We need to write some digits out. Then, there's one digit's repeating. That's what the book says to do, so let's do that. Let's multiply by 10 to the first power since one digit repeats. That would make this 8.333 repeating. Okay? So what would happen, let's see what would happen if I did 10n, I don't like this, 10n minus n, that would be 9n. That would be 8.333 repeating minus 0.833 repeating. All these would cancel out. I'd get a 0 here. 13 minus 8, I'd get 7.50 over 9. If I divide both sides by 9, I'd get n equal 7.5 over 9. I could move the decimal place over 1 on each of these, and that would be n equals 75 over 90. And then I could divide, let's see, 15 goes into 75 5 times, and 15 goes into 90 6 times. So it would be 5 over 6. Let's see if that's what we get in the book to see if I did it right. Haven't done this in a long time. Most of the time you don't have to do this anymore because you got graphing calculators. It is 5 over 6. That's exactly right. So what the book says does work. It says just however many digits are repeating, multiply the number by that many, 10 to that many digit power. So 10 to the first power. So that would be 10 to the first is 10. Multiply the number by 10. So 10n, and then if you do the 0.83 repeating by 10, it would give you this 8.33, and then you would come down here, and this is where you would actually subtract those two. Again, if you put 0.83 and you just 333 and just fill up like 20 digits or however many you can in your calculator, and you put math enter, it would probably give you this fraction, but that's how you would do it by hand is this method right here. I had to think a minute because I haven't had to do this since I probably was in school, and hardly anyone does it anymore with the graphing calculators. All right, 33 is a problem where you're just kind of playing around with numbers. If they want you to find two irrational numbers so that when you add them together, you get a rational number. Well, the easiest way to do that is to think about this. Square root of 2 is a rational number, and negative square root of 2 is a rational number. If I add those up, I get 0. So if I add them up and then divide it by 2, that would be 0, because 0 over 2 is 0. So I could add square root of 2 and negative square root of 2, and I get a rational number. So what this is telling us, it is possible to add 2 irrational numbers and get a rational number, but usually they're opposites, okay? And then the B part says for us to find two irrational numbers, A and B, such that A plus B is irrational. Well, that over 2 is irrational. That one is pretty easy. You could pick pretty much any two irrational numbers. Let's say square root of 2 and square root of 3. If you add those up, I can't simplify that. That's still an irrational number. So these numbers could be like square root of 2, square root of 3. You could have picked any two irrational numbers. Up here, you would need to pick a number and its opposite, and that would work.